Hi students, I am Praveen Sebastian Paul. In this lecture we are discussing the single precision floating point format or FP32 or IEEE 754 32-bit representation. A floating point variable can be represented in a wide range of numbers than a fixed point variable of the same bit width at the cost of precision. A signed 32-bit integer variable has a maximum value of 2 raised to 31 minus 1, whereas a IEEE 754 32-bit base 2 floating point variable has a maximum value of 2 minus 2 raised to minus 23 into 2 raised to 127 representation. All the integers with a 7 or fewer decimal digit and any 2 raised to n for a whole number can be converted exactly into IEEE 754 single precision floating point value. In IEEE 754 2008 standard, the 32-bit base 2 format is officially referred to as binary 32. It is also called single in IEEE 754 1985 format. IEEE 754 specifies additional floating point types such as 64-bit base 2 or double precision, and more recently base 10 representation are also a standard format in IEEE 754. The IEEE 754 standard specifies a binary 32 as having a 1-bit sign, 8-bit exponent and 24-bit significant precision. So this 32-bit is divided into 1-bit sign, 8-bit exponent and 24-bit significant precision. So these can be discussed with the help of an example. So my dear student, consider the example. We are going to convert the decimal number 12.625 into IEEE 754 single precision representation. In the first step, what we have to do is convert the decimal number into its binary representation. For the conversion of 12.625, let us consider the whole number portion 12. This 12 can be converted by continuously dividing 12 with 2, which will result in the binary number 1100. That is, the decimal number 12 is represented in binary as 1100. In the fractional portion, that is 0.625, what we have to do is multiply this fraction with 2 until the result will become 0. So that is 0.625 into 2 will result in 1.25. So in this 1.25, take the whole number portion, that is 1 into the result portion, and the rest portion, that is 0.25, should be again multiplied with 2. So 0.25 into 2 will result in 0.5. So we are taking the whole number portion, that is 0 into the result part, and the rest portion 0.5 is multiplying again with the 2, which will result in 1.0. So this 1 is taking to the result part and the rest portion is 0. So 0 into 2 will exactly result in 0. So the decimal number 0.625 can be represented in binary as 101. So that is, the final result is 12.625. The decimal number 12.625 can be converted into binary as 1100.101. So this is the first step, or the step 1 for the IEEE 754 conversion. In the first step, we had converted the decimal into the binary representation. That is, the decimal number 12.625 is representing in binary as 1100.101. In the second step, or the step number 2, represent the binary in the normalized or arithmetic or exponential form. That is, here we are dealing with a floating number 1100.101. The floating point should be shifted 3 times towards the left, which will result in 1.100101 into 2 raised to 3. So this exponent part 3, as we had shifted 3 points towards the left portion, that's why we are taking the exponent as 3. So this is the step number 2, representing the binary in the normalized form. That is, the binary number 1100.101 can be represented in normalized form as 1.100101 into 2 raised to 3. In the third step, we have to find the SEM factors, that is, sine, exponent and mantissa portion. The sign deals with which type of number we are dealing, that is either positive or negative. The decimal number 12.625, unless there is no representation of a sign, we can consider that number as a positive number. So the 12.625 is a positive number. Since we are dealing with a positive number, as we had discussed in the earlier lectures, a positive sign can be represented in binary as with the help of a 0 bit. So the positive sign or the sign for this number is 0. The sign bit is 0. Next, the second set is E. E is for exponent. As we had discussed in the beginning, in the 32-bit representation, the first bit is for the sign bit, or 1 bit is for sign bit. The remaining 8 bits are for exponent bit. So we have to find the exponent. Here, the exponent is calculated with the help of the power bit plus a bias value. In the case of 32-bit representation, the bias value is 127. So we have to add this 127 with the power value, that is, here the power is 2 raised to 3, that is, the power is 3. We are adding 3 with the bias value, that is 3 plus 127, which will result in 130. This 130 should be converted, 130 is a decimal number, this 130 should be converted into a binary representation, which will result in 1 0 0 0 0 0 1 0, that is 1 5 zeros and 1 0. And the third portion is the mantissa portion. Mantissa, which means the number after the exponent point. So the mantissa portion is 1 0 0 1 0 1. That is a fractional portion. So here we got the 3 set of values, that is a sign S bit or the sign bit is positive, that is we are taking the 0 bit. E is the E exponent, it is an 8-bit representation. Here we got 1 0 0 0 0 0 1 0, and the mantissa portion is 1 0 0 1 0 1. So finally we are going to represent in the 32-bit representation the number, the decimal number 12.625 can be represented in IEEE 754 32-bit representation as, so the first bit or the sign bit is 0. The 8 bits are for exponent, that is 1 0 0 0 0 0 1 0, and the remaining 23 bits are for the mantissa portion. Here we are dealing with the mantissa 1 0 0 1 0 1. So we had only 6-bit mantissa. The rest of the right side of mantissa should be put as 0. So this will be the final answer. So my dear students, hope you had understood this topic. So dear students, consider this assignment question. Convert the decimal number 25.125 into IEEE 754 single precision representation. So my dear students, in the upcoming lecture we will consider another example of single precision representation. So see you soon. Until then, goodbye. Thank you and all the best.